Okay, folks, good afternoon. So what we did last time, we wrapped up the paper on how to synthesize DC to DC power electronic converters. Then the next topic is a very short and brief discussion on power electronic semiconductor devices like diodes and MOSFETs and IGBTs. So we briefly talked about MOSFETs, diodes. Also, there's a homework assignment posted on Blackboard. Mistakenly, I put the due date to be on the 14th, but actually the actual due date is the 17th, which is next Tuesday. For on-campus students, there is also a sign-up sheet circulating. Just make sure you sign your name before you leave the class today. All right. Any questions?
Regarding homework submission, on Tuesday we have career fair, so can we submit?
So you can submit the homework earlier if you want. It doesn't. Any time before that 1:59 p.m. is fine. You can electronically submit it in a sense that you can scan your sheets and email it to me, or use your cell phone and take a picture and email it to me. Just make sure while you're taking a picture, your hand is not shaking and it's readable. So check the image before emailing it to me. Any form of submission is fine. You don't have to come to class and submit it, okay? Other questions? All right. So we are going to continue the discussion on diodes. So diodes are basically p-n junctions. An ideal diode conducts positive currents and blocks negative voltages. However, we don't live in an ideal world. We have so it's basically a second quadrant switch. Remember, a second quadrant switch could also be a fourth quadrant switch, assuming that you can just flip the component in terms of the polarity of the voltage and the direction of the current. Now, if you go ahead and go to the market and buy a diode, you are not going to get a volt-ampere characteristic like this. You are going to get something like this. So let me just write it down here: a real diode IV characteristic. Okay, so if the diode is conducting some positive current, there is a little bit of a voltage drop on the diode, which is called the forward voltage. Okay, ideally we want this voltage to be zero, but it is not zero in a practical diode. It's a number that you can actually look at the first sheet of the data sheet and actually see how much the forward voltage drop is. Obviously, it depends on the blocking voltage of the diode. It's a number usually between 0.4, and if it is a very high voltage diode, then the number grows basically. On the negative territories, we are good. Basically, it actually almost blocks negative voltages. But you get to a point that if you actually put excessive amount of voltage on your diode is going to basically go through a breakdown and most likely die. So this voltage is called the breakdown voltage. All right, so you should make sure that while you are using this diode in your real converter, you would not get close to this number. Again, this number also appears on the data sheet. So if somebody tells you I have a 200 volt diode, that 200 volt is referring to this breakdown voltage. And in a practical case, you shouldn't go beyond 150 or create have a little bit of a margin for yourself, a safety margin. The higher this breakdown voltage, the more expensive probably the diode is going to get. Forward voltage drop is going to grow if the breakdown voltage grows. So the forward voltage of a 80 volt diode is smaller than the forward voltage of an 800 volt diode, something like that. And probably the diode is going to get a little bit more expensive. Also remember, in all of these characteristics that we are going to draw, these are static characteristics in a sense that they are not representing any dynamic behavior, because diode you can actually model in a dynamic way. There are a bunch of capacitors in the diode, the minority carriers, and things like that. These are static diagrams in a sense that they have set the current or set the voltage to a particular point, waited long enough for the transients to be over, and then measured the voltage or current or whatever it is. So these are called the static characteristics. So if you want to model your diode, if you want to have a more accurate model in your diode, this VF is actually representing some losses in the system, right? So you can either just include VF, or you can also include a little bit of a slope over there, which is represented by a resistor. So the resistor is we have an exponential term over here. So this part of the graph is an exponential graph, but again, you can kind of do a piecewise linear and say, I have like a battery, and in series with the battery, we have a resistor. But to be simple, just as long as you have the average value of the current of the diode, if you just multiply it by VF, you have a rough estimate of the losses in your diode, basically. So that's why a lot of exercises you ask about what is the average value of the current that is passing through the diode, because that's an indication on the losses in your diode, basically. All right, there's another phenomenon that diodes exhibit, and it becomes important in power electronics, which is called reverse recovery. All right, so what is this all about? So presume you have a circuit like this. You have built a circuit like this in the lab. So you have like for instance, source of voltage. You have a switch. Kind of like a buck converter almost. All right, so this is just a test thing. So you have a diode that is forward biased, and a certain amount of current is passing through the diode, like I0 or I0. Then all of a sudden you close this switch and apply a negative voltage to your diode, so you're forcing your diode to go to the reverse bias area. And the way the diode exhibits, it looks like this. So for instance, we are measuring the current of the diode. Okay, so ideally you would expect something like this. So certain amount of current is passing, and then all of a sudden the diode is reverse biased, so it's zero. So ideally you would expect something like this, but in practice what you will observe is something like this. So the diode is conducting. Then the current of the diode gradually comes down. Instead of instantaneously coming down, it gradually comes down. Then it gets negative. And then it recovers back to zero. Okay? So even for a very short period of time, your diode is actually conducting in the opposite direction, which you do not expect to happen. Now, what I drew over here is almost an approximation. Depends on what diode you are making an experiment with. You may get actually different characteristics, but you pretty much expect that you have almost a linear phase during which the current of the diode is linearly going down to the negative territories, and then you have an exponential recovery kind of a phase. Okay, and this is, by the way, T naught. And this peak current is called IRR, which is called the reverse recovery current, this peak. So sometimes if you have a relatively extensive data sheet for your component that you have purchased, this I sub RR is mentioned as a function of the test that they were running, like what was the forward current and things like that. And this time period that the diode current is negative is called TRR, which is the reverse recovery time. And again, it is mentioned in the data sheet. So these are all mentioned given a certain test condition that the manufacturer has performed the tests, and they are indication on like how much energy you would lose in your diode and things like that, or how long it would take your diode to actually turn off. So you can associate several disadvantages to this phenomena, this reverse recovery phenomena. One of them is power losses. So we have basically charges, electric charge is going somewhere that it's not supposed to be going. The voltage of the diode is not, it is actually ramping up. So when you multiply the current by the voltage, you get some non-zero curves. So you may actually lose some power because of this. So the disadvantages are okay, let me do it again. One is loss of power. The other one is time delay. You're expecting your diode to be instantly off, but it is not actually off. So there's a bit of a delay, so you cannot push up the frequency so high. And the worst one is distortion in the waveforms. Okay. Distortion on other waveforms, on other current waveforms. And sometimes this distortion is causing a stress, some current stress on the other components. For instance, in the buck converter, if you look at the current waveform of the switch, ideally it is supposed to look like this, but in a practical converter, you are going to get a little bit of a hump over here. And this hump is because of the reverse recovery of your diode. Your diode is off, so negative current is passing through your diode, and that current is being added to the current of the inductor flowing through your switch, basically. So you get a little bit of a hump, and then you may say your current is distorted. There might be extra amount of stress applied to your component. All right, any questions? So if you're curious about why this happens, assuming that we are a little bit familiar with devices, the physics behind the devices, so technically it is because of the motion or the diffusion of minority carriers. Why does it happen? Okay, if you look at a diode, a PN junction that is forward biased, a structure like this, you're going to see that you have a bunch of electrons accumulated here and a bunch of kind of positive charge carriers accumulated, holes basically accumulated here. All right. Now, so this is when the diode is forward biased. Now, after the diode is reverse biased, you should see a structure like this. You should see more of these guys on the left-hand side. And more holes on the right-hand side. So there should be a transient or transition going on to go from forward bias to reverse bias in terms of the motion or movement or diffusion of these minority carriers. And that is actually causing the reverse recovery. Can we eliminate it? No, we cannot. This is just an inherent, feature of a PN junction. But there are ways to mitigate it. So solutions are, or the solution is, instead of using a PN junction, use a metal semiconductor basically junction. And again, we don't want to get to the physics of these devices, but as it turns out, if you have a junction, one part is metal, the other one is a semiconductor, these minority carriers are actually less effective. And those kind of diodes are called Schottky diodes. Or they're also called fast recovery diode. Okay, so if you're in the market, you're looking at data sheets. If you see the phrase Schottky diode or fast recovery diode, is actually a diode that in which the reverse recovery basically phenomena has been tried to be minimized, something like that. So pretty much all diodes that we use in power electronics, they are fast recovery diodes to minimize this effect. Any questions? Yes.
So for the reverse bias, would we not have more electrons that are getting attracted to the N side, like contrary to what is written in the power?
For the reverse bias, this is not showing the motion of the electric current or anything. This is just telling you at the place that the junction is happening, how the device is depleted, basically. This is the barrier that causes the device not to conduct, basically. You're saying that there should be more electrons going from N to P? Is that what you're saying?
If you apply positive voltage to the N side, so you would simply expect that, holes wouldn't generally come to the N side. So
what would come to the N side?
The holes wouldn't come to the N side, but that's what has been shown.
No, the holes would not come. Basically, there are electrons over here, and those electrons basically migrate and go over there. And that means when the electron is gone, there's a hole over there, basically, in the lattice of the device. Okay, so just a very, very brief discussion about reverse recovery. You can actually look at some device, books and exactly know what's going on. All you have to be careful about is purchase a device that has a short reverse recovery time. Or sometimes they represent this reverse recovery phenomena by some QRR, which is the amount of charge. So basically, the data sheet gives you this area over here, which is called QRR, the electric charge that is actually going in the opposite direction while the diode is trying to turn off, basically. All right, so the next component, so remember diodes were passive. They are switches. They are considered to be switches, but they are called passive switches. So let's now move on to an active switch, an IGBT. Okay, IGBTs are relatively newer devices. They were invented, I think, back in the 70s. There are certain number of people and certain number of research institutions that they claim that they invented IGBT first. So we don't want to get into that dispute. But anyway, if you want to draw one, you would usually draw something like this, pretty much like a transistor. It has a collector, it has an emitter, and then we call this guy gate instead of base, basically. It's a gate, basically. If you really zoom in into the device, you are going to see that there is a FET basically integrated with a transistor. So the way it works is, remember a BJT, a bipolar junction transistor, you always need to have a little of a base current, and that base current is amplified in the right-hand side of the transistor. Now, in a power electronic converter, you cannot constantly feed current to your system because that means you are going to lose some efficiency in your base because your gate driver constantly have to send current to the base. So you put a basically FET on the input side, so instead of actually constantly feeding it with some current, you're just applying some voltage from gate to emitter and the device is on, and then you don't have to constantly feed power to your base to be on. Basically, that is basically the whole trick. So this is basically the whole. These two are equivalent. So it is called a regular BJT. You can you can use a regular BJT as a power device, but it is a current controlled power device. But because of this innovation, you can actually apply some voltage from gate to emitter, and therefore your device is called a voltage-controlled power transistor. Okay. So if you look at the data sheet, if the voltage that is applied from gate to emitter is beyond a number, like more than, for instance, 10 volts, then your device is guaranteed to be on. If it is 0 or sometimes a negative value, like -5 or 0, then your device is actually turned off. All right, so what about the volt ampere characteristic? So if you look at the data sheet of an IGBT, you will see something like this. Okay. Okay, if the device is off, it is not supposed to be conducting anything. So you're pretty much on this line. So the device is off, it is not conducting any current, and it is capable of blocking some positive voltages from collector to emitter. However, you cannot keep increasing this voltage. There's going to be a breakdown happening at some point. And the device is going to get damaged, basically. Okay, so this is when you have not even triggered the device. The device was off, and it was blocking some positive voltages, but beyond a certain point, some breakdown mechanism happens. So this voltage is reported or named to be basically breakdown voltage. So for instance, when you buy a 600 volt IGBT, that 600 is referring to this basically parameter. That means while your device is off, you can expect your IGBT to tolerate 600 volts without breaking, basically, okay? Something like that. All right. Now, what about negative voltages? How about if I apply a negative voltage to my IGBT? Again, for a certain range, you're okay, and then the device breaks. Okay. So this is called, let me see. Okay. So this is called E to C breakdown voltage. All right. Or reverse breakdown voltage. Okay. So I'm just going to put a bunch of numerical numbers here. So for instance, you can buy an IGBT that can handle 600 volts, 1200 volts, 1800 volts, something like that. But this reverse breakdown voltage is usually small, for instance, only 18 volts. In most typical IGBTs, you are not allowed to apply a negative voltage across the device unless that negative voltage is only like 1 or 2 volts or something like that. Like you cannot apply negative 600 volts to a 600 volt IGBT, okay? So the device is not going to handle it. Although there are devices, IGBTs, that are actually recently being introduced to the market, they are a little bit more expensive, and they can also handle negative voltages as well, if need be, okay? So this is as long as the device is basically off. So this region is called forward blocking region. And obviously this is called reverse blocking region. And as I said, you should not expect your IGBT or your typical IGBT to have much of a reverse blocking region at all. Just assume it's zero. You shouldn't go to negative territories. So this is as long as we have not turned the IGBT on, we have not applied any excitation to the gate of the device. But what if we do? Now, if you do so, you are going to see a characteristic like this. The device turns on and actually conducts certain amount of current. And again, in proportionate with the amount of voltage that you're applying, your current is going to get higher and higher. All right? So this is when the voltage that applied from the gate to the emitter is actually increasing, your current is also increasing. These flat lines are called saturation region. Which we actually do not use in power electronics. Remember, in electronics, you are going to use these devices, these operating points, if you want to, for instance, amplify a signal. But the problem with this saturation region is the voltage of the device is not zero, the current of the device is not zero, therefore you are losing a lot of power in your device. So you don't want to do that because your device is going to get damaged. What you care about is just this region. All right? That the device is conducting positive amounts of current, but at the same time there is a little bit of a voltage applied across the terminals of the device, which is this VC on, or collector to emitter saturation voltage. this is like VF, the forward voltage of the diode. Ideally, we want it to be 0, but practically it is not 0. It's very small, like about 1 volt, 2 volts, depending on what kind of IGBT you are using. And this region is called the linear region. Okay, so this is actually where you would prefer to use your IGBT. All right? So sometimes when it comes to loss analysis, when obviously your IGBT close to ideal IGBT is off, you could say there's no losses because the current is 0 anyway. But when it is on, you can assume that your IGBT is almost like a diode, like a battery basically, with a voltage of VCE on. All right. So this is a very, very, very simple way of modeling your IGBT. When the IGBT is turned on, it is operating in the linear region. There is a small voltage appears from basically collector to emitter. You can actually measure it. It's about 1, 2 volts, depending on the blocking voltage of the IGBT. The higher the blocking voltage is, the higher this voltage is as well. All right. So if you want to idealize this characteristic, you may look at something like this. The device can handle positive voltages. Oops. All right, when it is off, no problem, no current will pass through the device. It can handle positive currents when it is turned on. And it might be able to block a little bit of a negative voltage as well. All right, something like this. We don't really use the IGBT in that mode anyway. So as you can see, IGBTs are first quadrant switches. Okay. So most of you guys know already, I just mentioned it a few minutes ago. But if you're curious about how we switch from the on state to off state, basically that is dependent by the voltage that apply to the gate of this device. And this is called the gate threshold voltage. Okay. So the data sheet also provides this number. It's, for instance, 5 volts. But you really want to go beyond this threshold a little bit, a couple of times more. Make sure your device is actually totally on and is deep in the linear region. So for instance, we apply 10 volts from gate to emitter, or 15 volts, sometimes 20 volts, depending on what kind of IGBT you are dealing with. And if you want to turn your IGBT off, you just apply 0. Or sometimes in some devices, you have to apply a small negative voltage, for instance, negative 5 volts or something like this. All right. Now, so remember, practically IGBTs by themselves do not have any diodes in them. But a lot of times, I would say like 99% of the time, when you purchase an IGBT, you will purchase an IGBT that is packed with a diode, basically. All right. So you can argue several ways why they add this diode. Later on, we are going to see a lot of times you need this diode. And at least what you can get out of this diode is to make sure no negative voltages are applied to the IGBT, therefore the IGBT is not going to get damaged, okay? So they are trying to avoid this area basically. As soon as you intend to apply a negative voltage across your component, the diode is going to turn on and it actually protects your IGBT from going to the reverse breakdown. So if you are trying to purchase an IGBT, either you can buy a discrete component, you can buy a copack, in which the anti-parallel diode is already added, or you can actually buy modules of IGBTs. Sometimes 2 of them are cascaded, or sometimes 4 of them are together in the form of an H-bridge, or sometimes 6 of them are together in a form of like an inverter, like a 3-phase inverter. Now, by the way, in case you have not seen an IGBT before, let me just show you, just Google it and see what we can find in terms of pictures. All right, so the ones that we are seeing actually, this particular one, you can see they are actually in the pack. We have 2 IGBTs and the 2 diodes as well. So they're actually, it's a module of IGBT. The picture, the way it looks to me like a 600 volts, 100 amp or 200 amp kind of a module basically. So IGBTs are relatively high voltage, high current devices compared to MOSFETs that we have not introduced yet. They are slower, although faster and faster IGBTs are coming to the market, but they can handle higher amount of power. So if you, for instance, have a high power motor, electric motor, you would definitely find IGBTs that are driving that electric motor, something like this. Let's see if I can find a small one that you may have not seen before. So they come in different colors. Usually they are black, and sometimes they exactly look like a MOSFET. This is like a very kind of a low power, like, I don't know, 10 amps, 20 amp kind of an IGBT, something like that. So do not be surprised if you see IGBTs like this. Let me see if there's anything interesting we should see or not, probably. All right, so let's go back to our IGBT description. Any questions? Yes?
I have one question. When I'm using IGBT as a switch, what's the input voltage I'm applying to that? Is it VCE?
What do you mean by input voltage?
For example, I'm connecting a battery to an IGBT.
Okay.
So the battery voltage will appear as a voltage across capacitors and collector and emitter.
Yes, for instance, let's say you are using this IGBT to build a buck converter. So your input voltage in the buck converter appears when the switch is off from collector to emitter. Okay? Was that your question? Huh?
Actually, what I want to say is, as per those plot, you said the VCE should be very less. VCE would be very less. And if VCE...
You're talking about this voltage?
Yeah.
Okay. Saturation voltage?
Not
or the breakdown
when
voltage?
It is conducting.
Oh, when it is conducting. Okay, VCE on. Okay.
So it goes from the active region to the saturation region.
Right.
Without much increase in the voltage.
Right.
So when I'm connecting a battery of 150 volts,
okay,
so will it go to the saturation region?
So your question is, if you get an IGBT and place a 100 volt battery in parallel with that, what happens?
Yeah.
So it depends on what kind of excitation you have applied to the gate. If you have not made any excitement to the gate, you are basically somewhere around here, 150 volts.
Mm-hmm.
Nothing happens. Assuming that your IGBT can handle like 600 volts, you're good. Nothing happens. But if you have made already an excitation to the gate and then apply that voltage, you shouldn't do that basically. Because if you have turned your device on, you should expect your device to conduct currents rather than applying any voltages to your device, basically. Okay? All right, any other questions? Yes?
So what is said here is that if I require a higher current to be flowing in the circuit, I would generally go for basically a higher VGE. I mean, if my circuit requires that my current be higher than linear.
Okay, okay. See, as I said, we never use our IGBTs in these areas, right? We only use them here.
Yeah, so let's say.
All right. So if you use them here, like the threshold voltage that you have is about, I don't know, let's say 5 volts, and this gives you this 5 volt thing, for instance. All right.
So there's a particular restriction to the current with just 5
That
volt
is
applied.
true. That's why you always apply like 10 volts, 15 volts, 25 volts, or whatever, in a sense that your device is deeply in the linear region. Therefore, your current can go as high as 100 amps, 200 amps, something like that. But there is a downside to doing that. If you apply too much voltage to your basically gate, so technically, if you can assume that in a very simplified way, you basically have a capacitor over here, and that's why we kind of draw a capacitor here. You kind of have a capacitor internally, let's say imaginary capacitor, connected from gate to emitter. If this capacitor is charged to, let's say, 10 volts or 15 volts, your device is on and then can handle hundreds of amps or something like that. If this capacitor is discharged or the voltage of this capacitor is 0, the device is off. Okay. So the more voltage we apply to this capacitor, we are guaranteed to be able to handle higher amounts of currents, which is good, but at the same time, the losses in this capacitor sometimes becomes big. Remember, every time that we charge and discharge this capacitor, we are losing certain amount of energy in this capacitor. So if I push up, instead of applying 10 volts to my IGBT, apply 20 volts, the losses in the gate by itself is going to get quadruple. And the gate driver has losses, and you're going to lose some energy over here. So you realize you're losing, for instance, a couple of watts just in the gate signal, basically. So the more the better, ideally, but at the same time, you're actually increasing to the losses to the system. Any other questions? Okay. So now let's move on to MOSFETs, or basically power MOSFETs. There is not a significant difference between a MOSFET and a power MOSFET. It's just designed for higher amounts of power. All right. So we have N-channel MOSFETs, P-channel MOSFETs. Most of the times in power electronics you use N-channel. And there is a little of a capacitance kind of here going on. So they have two kind of parallel plates indicating on the input side from gate to the source, you kind of see a kind of a capacitance behavior. So this is the source, this is the drain. And by the way, for IGBTs, sometimes they also use drain and source instead of collector and emitter to make it a little bit compatible with MOSFETs. And this particular one that I drew is N-channel. And then we have enhancement or depleted MOSFETs. We don't want to get into the details of that. One thing that I want you guys to note is, as I was drawing this guy, I also drew the diode as well. So as it turns out, while you're making a MOSFET, whether you like it or not, you're also making this diode. You cannot ever eliminate this diode. The diode is always there. It's called the bulk diode, okay? All right, or the body diode. Or the anti-parallel diode. So you can actually purchase an IGBT in which there is no diode placed in parallel. That's the decision of the manufacturer. But you cannot buy a MOSFET in which this diode does not exist. This diode is always there. Always remember that. So in terms of IV characteristic, So this is the current of the drain versus the drain to source voltage. Okay. So if the diode is, if the device is off, it can actually block some positive voltages to a certain point till you reach VDSS, and the device breaks. So it's called the drain to source breakdown voltage. All right, so when you purchase a, let's say, 150 volt MOSFET, that 150 is referring to this voltage, to this breakdown voltage. Now, technically, you cannot apply any negative voltage across this component because the diode is there, and as soon as you intend to do anything negative, the device is going to basically, the diode is going to turn on. Now, what if you apply some signal or some voltage from gate to source and you manage to turn the device on? It actually behaves like this. Something like this. All right? So technically, you are using your device in this region. Okay, and that is kind of, it behaves like a little bit of a resistor basically. So the more the current, the more the voltage drop is. But this resistor is very small. This is an exaggeration here. The resistor is in the order of like milliohms, like 10 milliohms, 100 milliohms, you know, depending on the voltage level of your component. Now, one thing to remember is that MOSFETs themselves are very, very symmetric devices. So in the negative territories, we almost have the same behavior. Assuming this diode was not there, but the diode has its own characteristic, you know, which is this, for instance. So in the negative territories, there is a competition basically going on between the device itself and the diode. If the gate signal has been triggered, the device is eligible to conduct negative currents. The diode is also trying to conduct negative currents. So whoever wins is basically the one that exhibits lesser voltage. So this is for the diode. Okay. And most of the times the power MOSFET actually wins because it exhibits a smaller voltage across its components. All right, so if you want to idealize this device, you will get something like this. So it can conduct positive currents when it is on, and obviously it's controllable or controlled. Control meaning that you can actually turn the device on or off using the gate. When the device is off, you're here. And you can also conduct negative currents in your device. And this one could be uncontrolled, meaning that you have not applied any gate signal to the device is off, and the negative current that is passing through the device is because of the diode. Or you can actually turn the gate on, and the competition happens, or you can basically have a little bit of a control over it. So it's up to you which one you want to use. Now this region is not necessarily very popular. In a lot of applications, you tend to use your MOSFETs the same way that you are using your IGBT, which is a first quadrant switch. But technically, you can use your MOSFET as a device that can handle both positive and negative currents. And we're going to talk a little bit about this when we talk about synchronous rectification. All right? In terms of modeling, so by the way, the device is called a current bidirectional, voltage unidirectional device. Two-quadrant switch. And in terms of modeling, when the device is on, when it is off, you can model like an open circuit. When the device is on, it almost behaves like a resistor. Which is called RDS, the resistor that appears from drain to source. That resistor is actually representing the slope of this line. Okay? So remember, when an IGBT is on, it is pretty much behaving like a constant voltage source, like a saturation voltage value of, like, for instance, 1 volt or 2 volts or 1.5, something like this. When your MOSFET is on, it behaves like a resistor, and the value of this resistor obviously depends on your device, but to give you some ballpark numbers, like 50 milliohms, 100 milliohms, 150, 500, something like that. It's in the order of milliohms. It's not that much. One other interesting thing about MOSFETs to remember is, as the device gets warmer, this resistance that is representing the device when it is on actually increases, which is unusual usually. So the temperature coefficient is positive in a sense that if the device gets warmer, the value of this resistor also gradually increases. And because of that, this is actually quite good. You can easily place MOSFETs in parallel. Parallel, something like this. Okay, so what do I mean by that? So let's say you have two MOSFETs. Like each one of these MOSFETs can handle, for instance, 20 amperes, but in your application you are looking for 40 amperes. So the indication is you should purchase two of these MOSFETs and place them in parallel with each other. Now the concern that you may have is, internally, even though they are coming from the same manufacturer, they are the exact same model, there might be a little bit of a difference from one to the other. For instance, one of them may exhibit for instance, 10 milliohm resistance as RDS on. The other one may exhibit a 9 milliohm resistance. Okay. So you're worried that the current of 40 amperes is not evenly distributed between the two MOSFETs. One of them is actually conducting more than the other because one of them is exhibiting a smaller resistance. So for instance, here you're going to realize that there is going to be more current going down the 9 milliohm resistance versus the 10 milliohm resistance. So more current is going through the 9 milliohm resistance. It is going to get warmer therefore because there is more losses associated with that. And because it gets warmer, it actually increases faster. So you get to a point that this is like 10.5 milliohms because they are both going to get warm anyway. But the 9 milliohm one is going to get warmer and therefore it's going to rise more. So they kind of adjust it between themselves to the extent that ideally you would like them to be equally dividing the 40 ampere current between themselves, 20 amps and 20 amps. So that's a good thing. But imagine if it was the opposite way around, the device that was getting warmer assumed that it had a negative temperature coefficient. 9 milliohm would even reduce down to 8 milliohm, so there is even more current going through that, and then it's going to get even warmer, so in the end all of the current is going through that right-hand side transistor, and it's going to basically kill it. So that's actually a good feature about MOSFETs, that you can easily put them in parallel without worrying about, significantly being worried about a non-even current distribution between the two devices. All right, any questions? Okay, so to summarize things, we talked about diodes. They are passive switches. They don't have a control terminal, and they are actually a second quadrant switch device. Or you can flip them and turn them into a 4-quadrant switch, basically. We talked about IGBTs, and they are first quadrant switches, and then you can flip them, that they turn into a 3rd quadrant switch. And then MOSFETs are actually mostly used for the 1st quadrant, but they can also handle the 4th quadrant as well. All right. So far in this class, yes?
When the temperature increases, the resistance increases, right? So the characteristic curve will also change a little bit.
That's right. That is right. So yeah, if you want to talk about the effect of temperature on this characteristic, you can actually get a PhD degree. How this characteristic is going to change by temperature. You're right. But yes, the most obvious observation that you may have is the slope of this RDS on is going to change. That's right.
It will basically lower the slope, right? It will turn to
the resistor is going to get increased, therefore it is going to, let me see.
It will lean towards.
Yeah, it's going to get actually further to the left, something like this. So it's going to become, I'm sorry, if the temperature increases, the slope is going to get, well, it's a little bit confusing for me. It's going to go the other way around. Something like this. So it's going to be deviate from the ideal form. Right.
And in terms of IGBT, we can say that its resistance is 0 because it's vertical.
You can almost say that. Again, depends on at what level you're trying to basically model your device. You can argue that the very first simple model that you're representing, you can say this line is almost in parallel with this. So the resistance is 0. But then you can argue that some people also add a little bit of resistance here as well. But honestly, I haven't seen any data sheets representing a number for this resistance. If you really want to be super accurate, you also have to put a resistor there. But in terms of losses, most of the losses are happening here, which is because of this part. All right. So yes, in the first step modeling approach, you can say it is almost, when it is on, it is almost like a battery, basically. Something like this.
You didn't say much about a reverse voltage on a MOSFET. Is that problematic? I mean, if let's say it's faster than the diode can react, would it damage the MOSFET? Or
usually not. I mean, the diode is... the mentality is because you have the diode here, you should never expect your MOSFET to block any negative voltages. So in the system that you're designing, you're trying to avoid that scenario, because as soon as you tend to get there, the diode is going to turn on. So it's not something that you really have to worry about.
So it shouldn't damage the MOSFET with a reverse voltage spike.
Yes, that's right. That it doesn't damage it. The diode is taking care of that, basically. Although you can argue that if you damage the diode, you have killed the whole thing, because the diode and the MOSFETs are not separated from each other anyway. But I wouldn't worry about it. It doesn't really kill anything. All right. Any other questions? So we have looked at some topologies throughout this class. We have looked at some switches. Now we are going to talk a little bit about switch realization. I mean, how is it that, for instance, we look at a buck converter and we see, oh yeah, this is a transistor here, this is a diode here, or something like that. So let's talk a little bit about that. So let's just start with the simplest converter that we are familiar with, which was the buck converter. So remember, we are going back to the single pole double throw switch concept. Okay? So none of the devices that we have studied so far, like diodes or the IGBTs or power MOSFETs, they are not single pole double through switches. They are all single pole single through switches. So I have to redraw this using single pole single through switches. So this is one of them. And this is the other one. Okay. So I'm doing this, I'm breaking down my single pole double through switch to two single pole single through switches to be able to see which one should be a diode, which one should be a MOSFET, and things like that. So now I have to determine some polarities. So for instance, I know that my inductor current is, for instance, positive in the direction that I have identified, meaning that the power is always coming from the left-hand side and being delivered to the right-hand side of the topology. Now, these polarities are optional, but remember we have to follow the passive sign convention. So if I assume the voltage is in this, then the current is flowing from top to bottom. Now I'm assuming that this is my other switch, and then this is the current of that switch. All right? All right, so I'm assuming that the inductor current is positive. But later on, we can actually look at another case that it may not be positive, meaning that we are looking at a bidirectional converter. So assume okay, the inductor current is positive, or unidirectional power flow. Okay, from left to right. All right, now let's look at the switches. Switch A and switch B. Okay, now keep in mind the operating conditions of the buck converter. Switch is on, switch is off. When the switch is on, it is conducting positive currents because it's the inductor current. When it is off, it is actually blocking your input voltage that is positive. So if you look at operating conditions of your device, your power electronic converter, you realize that assuming that the inductor current is positive, your switch, when it is on, it is conducting positive currents, and when it is off, it is blocking positive voltages of the source. So we need a single quadrant switch, first quadrant switch. Okay. Now, it didn't matter how I assumed the original polarity of VA was. So, for instance, I could have done it this way. Assume that this is VA, and then following the passive sign convention, this is IA. And then you would realize VA is negative, IA is negative, therefore you need a third quadrant switch, something like that. But it doesn't really matter because in the end it's an IGBT or a MOSFET, basically. You just have to flip the device. All right, now let's take a look at switch B. So when this switch is on, it is conducting the inductor current, so IB is positive. I mean, showing the polarity that I have shown, the direction that I've shown for IB. But then when the switch is off, it is actually blocking the input voltage in a negative way. Therefore, we are looking at a second quadrant switch. Okay. The candidate that we had for the second quadrant switch was a diode, basically. The candidate that we had for the first quadrant switch was an IGBT or a MOSFET. All right. So technically, you can implement your system. Obviously, you have seen a buck how it is implemented, but in a more complicated converter, let's say you haven't seen it before, this is how it's going to look like. All right. Okay. So this is the trend in power electronics. First, we designed a converter, assuming that we don't know anything about the switches. How is this switch realized in a physical world? We don't know. We just know that it is a switch that sometimes is connecting the top throw to the pole, and sometimes it is connecting the bottom throw to the pole. Then we analyze the system. For instance, we look at the direction of the current of the inductor and things like that. Then we focus on each individual of the switches and see, okay, is this switch conducting positive current or a negative current? Is it blocking a positive voltage or is it blocking a negative voltage? And then from there, you are going to look at your library of the switches that you have, and there's not a lot of options. Either you are looking at a second quadrant switch, which is a diode, or a first quadrant switch, which is an IGBT or a MOSFET. The other thing that you have to be careful about is at least one of these switches that you end up having in your single pole double throw configuration has a control input. If you end up with two diodes, then the question is how am I going to decide which diode is on and which one is. So at least one of them need to have a control input. Now, so this is how you realize a buck converter. Obviously, you have seen it in a classical, power electronic class. Although I can argue that I can use two MOSFETs to build this thing. All right, this is the top MOSFET. And this is the body of the second MOSFET. All right, so this is still gonna give you a buck converter. And remember, MOSFETs always come with a diode. So this is always there. But we never use it because the current never changes its direction. And in the bottom, you also have a MOSFET that you may or may not use. Let me see if I can make this a little bit thinner. Something like this. So the components that you have in black are actually what you really need, but they come with the components in red. This diode you never have a use for it because this current never changes its direction. Okay, so the current is always positive. There's no way this diode would be on. However, in the bottom switch, you can argue that if I don't apply anything here to the gate of this bottom MOSFET, the body diode of this MOSFET is actually the diode of my converter. Although I can also command this transistor to be on at a good time, and instead of directing the current through the inductor current through the diode, I can direct the current through the MOSFET basically. So you can actually have two options. Either you can say, when this bottom throw should be conducting, I can use the diode to conduct the current, or I can command the MOSFET to turn on, and then it's the MOSFET that is actually conducting the current. Okay, assuming that you are actually turning the MOSFET on. Now, this technique is called synchronous rectification, and this particular topology is called synchronous buck. As it turns out, in terms of losses in the system, it makes more sense to turn the diode on, to turn the MOSFET on rather than the diode. Because in high current applications, for instance, your current is, for instance, 50 amps. And you look at the numbers, if the diode conducts that 50 amperes of current, your losses are, for instance, 2 watts. If the MOSFET conducts that 50 amperes of current, your losses are only, for instance, half a watt. So it makes more sense to turn the MOSFET on. So you can actually, save some energy by, it's called synchronous buck, because you also have a synchronized signal for the bottom one. So in terms of gating signals, let me draw it, make it a little bit more complicated. All right, so I'm going to call it switch 1 and then switch 2. So switch 1 is turned on and off like a regular buck converter. Okay. Switch 2 should be the complement of this. But remember, the switching instances are not, immediate. So what you do is okay. So when the top switch turns off, ideally at the very same time instant you should turn the bottom switch on, but it's almost impossible because if there's a little bit of an overlap between the conduction, you are going to provide a short circuit path when both switches are on, therefore you're shorting your input voltage, and that's not good. So what you do is you create a little bit of a, kind of a dead band over here. During this dead band, the diode is actually conducting. So actually your conduction is actually the green path. But then it is safe to turn the bottom switch on because the top switch is totally off. And when it is on, the MOSFET wins the competition from the diode, and then your basically conduction path is the blue path. So your current for most of the time is passing through the bottom MOSFET. Therefore your losses are minimized. Then when you get towards the end, you got to do the same thing. You turn this MOSFET off, so you block this blue path of conduction. So now the current is passing through the green path. And then you turn the top switch on anyway, and the bottom diode is reverse bias, and then the current is going to switch to the top switch, basically, something like that. So this is called synchronous buck because you have to synchronize this signal with respect to the top signal. It's called a synchronous buck converter. All right. I think we are running out of time. I'm going to stop here. What we are going to do next time is we just looked at the buck converter, and I kind of broke down the single pole double through switch over here to this switch over here to 2 of these single pole single throw switches. Now we are going to do the other way around because pretty much all the converters that we have seen so far have at least one single pole double throw switch in them. So what we are going to do is we are going to use the elements that we are familiar with now, like the diode and the IGBT and things like that, to build single pole double throw switches, and then use those single pole double throw switches whenever we want them. All right, so I'll see you guys next week on Tuesday.